Hey, Charles.
Hey, Michael.
We've got a quick little mini topic to talk about, which I'm calling messing with rewards.
Okay.
And so just to give you a sense of what that's about, I mention Ing Harada and Russell, who are they wrote a paper that covers the ground that I'm going to talk about. And then to make it more vivid, I drew a picture of me messing with a reward function. And when I asked Google for a picture for this is what it came up with. So that's Deborah messing, winning an award.
And that seems absolutely appropriate. She's got the same look on her face that you had on yours.
I know. That's what I thought. That was really interesting. I was surprised that Google did such a good job. I think image search is getting better because of machine learning.
Probably reinforcement learning. I hope you gave it a little reward.
Oh, I forgot to do that. All right, I owe it one. So I wanted to start off with a question to you, which is if we're going to be tinkering with the reward function, why might we want to do that? Why might it make sense to take a reward function for an MDP and then turn it into some other reward function?
Because it's easier.
It's easier to change it than to not change it.
No, just we might get a reward function that's easier to solve. And since the whole point is to solve the MDP, we should just make that really easy.
Yeah, so if we can find a way of changing the reward function in a way that makes it easier for the learner to work with, then and without actually changing what it's going to learn as a result, that's a win.
Oh, I wasn't going that far. I just figured we'd set the reward to 0 everywhere, and then everything would be easy.
Ah, that would make it easy, but I think it should be easier to solve and similar to what it would have learned otherwise.
Okay, I guess that's fair. That seems like less cheating. But it does invite a question. Maybe we don't want to get into a philosophical discussion here, but where did the reward function come from in the first place? I mean, I think the way you pose this question sort of suggests that there's a true original reward function.
That's a good question. So, so why might we want to change the reward function? Because we don't have one yet.
Right.
I think that's a really good point, and you're right. I'm not going to get into that, but this is a topic that you know that I have a lot of interest in because you and I have been meeting on this subject for a year or so, trying to figure out if we think about reward functions as being ways of encouraging reinforcement learners to exhibit certain kinds of behavior, then they're kind of like a programming language. They're kind of like a way of specifying behavior that then is going to get compiled by the learning algorithm into actual behavior. And so there isn't actually a lot of work on on how to do that. If we have some idea of what behavior we want, what reward function would be appropriate to make that happen. So you're right. So in some sense, I'm finessing that question and instead saying, yeah, somehow we have a reward function and we want to tinker with it, maybe to make it easier to solve, maybe to make it easier to represent, or easier to reason about, or any of a number of possible reasons, but without actually undermining what it is that the behavior is supposed to be that's being specified by that reward function. Because as you said, it's really easy to just turn the reward function into all zeros, and then all policies maximize that reward function. In which case, learning is done.
Yeah, and then we solved a problem, just not necessarily the problem we're trying to solve.
Yeah, that's right, and that's always an issue in AI. I think is we have to worry about turning the problem into an easier problem that isn't really interesting anymore.
Right. So, by the way, something you said made me think about something. Well, two completely unrelated things. So, you called a reward function sort of like a programming language. I like that. One nice thing about that is it let us think about this easier to solve thing while still being similar, saying, well, if you have a program that allows you to sort, well, there are many different programs that could allow you to sort, and some are actually more efficient than others. And they're more efficient both in terms of the time it takes them to run, more efficient in the space that they use, and they're more efficient in the sense that they're easier for a human being to write or to think about, even though they're ultimately going to exhibit the same behavior, which is sorting a list. So I like that. And then it makes the question of why would we want to change the reward function make a little more sense. And that ties into the second thing I wanted to say, which is you say easier to solve, but you haven't said what that meant. I could think at least two things it could mean. Easier as in faster, or easier as in might be solvable at all. Like there may be a reward function that becomes extremely difficult to solve.
So I summarize what you were saying to me as, first of all, if we think about reward functions as a certain way, we at least gives us an idea of what semantics is. Like, what is it that we want a reward function to make the agent do? And at the moment, we're going to finesse that and just say, well, whatever it is that the old reward function made it do. But then we can also think about changing it in a way that doesn't change the meaning, but does make it more efficient, either in terms of the amount of data it needs to learn or the computation that it needs to learn. I mean, I guess speed really has those two different pieces, right? One could be how much experience does the agent need, and then how much computation does it take to actually carry out the learning process. And that could be easier or harder. If you don't have to plan ahead super long, then it might actually be faster in terms of computation. And other kinds of efficiency include space, sort of the complexity of writing down the reward function, and maybe whether it makes a problem solvable at all. Maybe the efficiency is the difference between infinity and not infinity.
Yeah, which is a pretty big difference most times. I mean, in the limit.
So good. All right. So let's think about some ways that we can actually change the reward function without changing what it is optimizing. So how can we change the MDP reward function without changing the optimal policy? So in an MDP, we usually define it with the states, the actions, the rewards, the transitions, and our friend gamma. What we're gonna mess with here is the R, but we're gonna leave everything else the same. So what are some ways that we might be able to change the reward function that actually wouldn't change what the agent would want to do to maximize the reward function?
Well, there's a couple of, I think, obvious ones. So one is if you just take the reward function and multiply it by any positive constant, everything should be the same, right?
Yes, exactly so. So in some sense, the rewards are kind of unitless. So if you multiply them by 1,000, it still encourages the same behavior. It just seems like you're making more reward points, but they're not. It doesn't change the relative strength of different behaviors. So good. Okay, that's definitely one.
And I want to say this is true. Just like by multiplying by a positive constant doesn't make a difference. It seems to me that if you just shifted everything over by 1 or by 2 or by 3, it would make a difference. So adding a constant to the reward function, adding a constant as opposed to multiplying a constant.
Good. Okay, good. We'll talk about that one as well. And there's a third one that we're going to talk about that may not be so obvious, but do you have any other guesses?
This makes me think it desperately looks like what we did in the other machine learning class with clustering. There has to be nonlinear ways of messing with the reward function to get you the same answer, but I can't think of a compact way of saying what I'm thinking.
Okay, so that's fair, and we'll get into that in more detail. Ultimately, we're going to call it potential-based modifications or potential-based rewards, and I'll define that in a bit. But first, I want to go through as you pointed out, the simpler cases and develop a kind of methodology for proving that that we're not going to change the optimal policy.
Okay.
Okay, let's look at multiplying by a positive scalar. So I started out by writing out this equation Q, which you recognize as
the usual thing.
The Bellman equation. So let's imagine we've got some reward function R, and it therefore has a corresponding Q function, or solution to the Bellman equation. And this is going to tell us how to behave. If you know the Q function for a given reward function, then for each state, you're going to take the action that maximizes the Q value in that state. So this is kind of capturing, everything we need to know if we knew the solution here. But now what we're going to do is we're going to generate a different reward function, R prime. So R prime is going to be defined as, well, the old, R prime for a given state action pair is going to be defined as the old R, the old reward function for that state action pair, multiplied by a constant. And that constant should be positive. Why should it be not 0?
Well, if it's 0, then everything's the same.
Yes, if it's 0, then we shouldn't expect any of this to work. If you multiply all the rewards by 0,
you lose all information.
Yeah, very good. And negative, what do you suppose would happen with a negative?
I'm going to say the opposite of what you want, except I'm not sure what opposite means in this case.
That's right. It kind of flips reward and punishment. So then you end up trying to find the reward function that maximizes pain, which, could be an interesting exercise, but I think not what we're trying to do in this case.
Yeah, it's just like grad school.
I don't think the sign is flipped for grad school. I think it's just...
Oh, I'm pretty sure the sign is flipped for grad school.
All right. So here's what I would like you to do. I would like you to make a guess as to if Q is the solution to this original Bellman equation, and R prime is our new reward function as a function of the old reward function. How can we write the new Q function corresponding to this R prime as a function of the solution to the old Bellman equation with this Q? So I want Q prime SA in terms of QSA. And that's going to give us some insight as to whether or not we have a monotonic transform, that the action that was best before is still best now. So this one is intended to be kind of a warm-up. So you might want to go just with your intuition on this. So what would you think the value of Q prime SA is as a function of QSA? Now, keeping in mind that we scaled all the rewards up, think of it like by a factor of 1,000.
My intuition about that is actually pretty straightforward. What I want it to be is just, I want Q prime of SA just to be C times Q of SA.
In other words, if we double all the rewards, it should double all the Q values. If we halve all the rewards, it should halve all the Q values, that sort of thing.
Right, and that makes sense, at least to me conceptually, and nothing else. Reward is your reward, and the Q value is the kind of true reward you get, the sort of summation of all the rewards you're going to get. So if I double the rewards, I should double the value.
Yeah, that's good. So that is the right answer, and I just want to go through a quickie derivation to show why that's the case. All right, so here's how I like to think about this: is what we want to show is that our Bellman equation for Q prime and R prime is correct, that it solves and we get a solution to the Bellman equation. And since the Bellman equation is unique, the solution to the Bellman equation is unique, then we must have found the right solution. So what I did here is I took, imagine the Bellman equation for Q prime. It's like Q prime SA equals R prime SA plus gamma blah, 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 Q prime. All right. So what I'm going to substitute in here is our guess as to what Q prime is. So that is here and here. And our definition as to what R prime is, which is that. Okay. So if this is true, then we have a solution to the Bellman equation.
Right, and it's trivially true.
Right. And so why is this true? Right, because the C here, we can pull it out of the max. That doesn't, again, because C is positive, it doesn't influence the max. If C were 0 or negative, it would mess up the max. But we can factor it out of the max because it's positive, so it doesn't change the order of what's largest. It's going to then get multiplied by these C's, and it's inside the sum, but it's common to everything in the sum, so that gets pulled out there. So we actually get to move this C all the way out to here. And now notice that we can factor it out from, it's obvious now, I guess, right? So we can just factor the C out from both sides and they cancel. So what we are left with is this equation, which is the Bellman equation that we had already solved. So this has to be true. So the original thing has to be true.
Right. That makes sense.
Yeah, which is probably the way you would think about it.
Yeah, in fact, it's exactly the way I would think about it.
Awesome. All right, so now that we have this down, we should be able to do these other modifications, these other messing arounds with the reward function next. All right, so the next thing we said we would do is consider adding a scalar. So again, I wrote the Bellman equation for some reward function R. So this is the target behavior if we use R as our reward function. And now we're going to replace R with a new reward function, R prime, which is the old reward function, plus this constant C. So now on every step, we get an additional C reward that we wouldn't have in the original thing. So what does that do to our Q function? What's our new Q function as a function of the old Q function and this value C?
It'll be different from Q of S of A. Are you going to tell me the answer?
I will, but only after we do this as a quiz.
Okay, fair enough. All right, so it's just like what we did before, except now we're adding a constant. So I suspect we ought to be able to use similar reasoning to get to the right answer.
So can you think this through?
I think I can think this through. So when we did the last one, you did a kind of derivation. I didn't really talk about how I came up with the answer that I came up with, but I did it basically by just substituting a few things in my head and seeing if it worked out. So when we did the multiplying one, I said, well, all you're doing is multiplying R of SA times C. And since the sum of all those T of S of A, S prime times the max of A primes of those Qs can be unrolled as a series of rewards. That means all you're doing is multiplying all of those rewards by this constant C. And so I could take it out. And that's how I ended up with C times Q of S of A. So I think there's a similar argument here. So see if this argument makes sense to you. If we took the equation up top and we said, well, what's Q prime S of A equal to? Well, it's equal to R of S comma A plus C.
Right.
All we're doing is adding a C.
Right.
And then inside that sum, if we unroll the Qs, it's just going to be a series of all the rewards that we see, each time adding up a C. Mm-hmm. And so we could sort of separate out the adding of the C each time. And the problem with that is that each time it's being multiplied by gamma. So what we're seeing is a bunch of C's added over and over and over again. Mm-hmm. I mean, an infinite number of times, potentially. But each time multiplied by gamma, then gamma squared, then gamma cubed. But that's okay, because we actually have a formula for that.
Good.
It's the geometric series.
Yes.
And that's just 1 over 1 minus gamma.
The sum of the gammas is that.
And then you multiply it by C.
There we go. All right. So you're saying that the new Q function should be essentially the same as the old Q function, which has already kind of gathered up all the rewards, the R rewards,
Hmm.
but we need to modify it by this infinite sequence of C's, which is C over 1 minus gamma.
That is what I'm saying.
Awesome.
Is that right?
That's yeah.
Huh.
So let's do the proof. So again, the trick is going to be we're going to write out the Bellman equation for Q prime, substituting in our guess for Q prime and our definition of R prime, and then see if it works. All right. So this is the thing that we need to be true if the rest of it is true, right? That is to say, if it's the case that the new Q function is just the old Q function then shifted by this C over 1 minus gamma, then we need this equation to be true. So this is true if and only if what? Well, we have this C over 1 minus gamma inside the max getting added to this QS prime A prime. How does that influence the max?
It doesn't affect it at all so long as C is positive.
Even if C is negative, actually,
Oh, you're right.
because it doesn't depend on A at all.
It's a constant.
It's a constant. So we're adding this constant to all the different pieces of the max. So then the actual max that we get at the end of that is going to be whatever the max was before plus this same constant. So we come out of the max, but we're still inside the sum with the transition probabilities. So what happens to the transition probabilities here is this gets multiplied by this just as before, plus it's also getting multiplied by this, but this is a constant. It doesn't depend on S prime or anything like that. And the sum that we're taking is a bunch of coefficients that all add up to 1. So really, this whole piece here is going to get promoted all the way out of the parentheses, with the only difference that it's going to get multiplied by a gamma. So what we've really got here is a C plus C gamma over 1 minus gamma on this side, and a C over 1 minus gamma on this side. So in fact, here, let's do this. As a step, this is true if and only if this is true, which I got by subtracting from both sides the solution to the original Bellman equation.
Right.
Right? We've got this Q, we got the R, we got this thing here, and all that's left are these C things. So is this true?
Yeah, it is.
And why is that?
Because you multiply everything times 1 minus gamma.
Oh, good idea. So this is true if and only if this is true, where we've multiplied through by 1 minus gamma. And this is true.
Right, because
we've got this C on both sides, and we've got a C minus gamma and a C plus gamma. No, sorry, a negative C gamma and a positive C gamma that cancel.
Right, so C equals C. Whew, that feels good. We solved everything.
Not everything. So we handled the two relatively easy cases, though that second one I admit was a little bit more of a workout. The next one is going to be conceptually trickier, but the algebra is not going to be much worse. And this is going to be in the context of reward shaping. So have you heard this phrase reward shaping before? It comes up often when people are talking about, wow, how did they train that dolphin to jump through a hoop? So it's tricky to imagine how you might have gotten a dolphin to jump through a flaming hoop out of the water and then splashing down on the other side, because it's not the kind of thing where if you were going to train it, well, you can't tell it what to do because they tend not to listen unless you go, and you can't reward it just for having done the right thing, because if you have this flaming hoop up in the air and you just wait for the dolphin to jump through it and you give it a treat, +1 if it does it, and otherwise you just don't give it a treat, it's never going to figure that out. It's never going to inadvertently kind of hop through that hoop and say, hey, do I get a reward? So how do you suppose they actually train dolphins to do this?
I have no idea, but I'm going to guess about how they do this because I'm not as into dolphins as you apparently are. And so I'm assuming what they do is they have to coax the dolphin to jump through the hoop in the first place by making it worth his or her while to do. So you kind of reward it maybe for jumping first and then getting near the hoop without the fire, with the fire. You just keep giving it, kind of rewards for getting close enough until it, rather than inadvertently jumping through the hoop, decides that must be the right thing to do now.
Yeah, I think that's some approximation of what I imagine that they do. My understanding is that they'll start off with something like, you put the hoop in the water and you put a fish next to the hoop, right? So that the dolphin swims over and eats the fish. And then you start saying to the dolphin, you start changing when you pay off the dolphin. You don't give it fish for just touching the hoop or for being near the hoop. You give it a fish for actually touching it with its nose. And then you lift it out of the water a little bit, and then it has to, swim faster to get up to it. And then you lift it out of the water a little more, and it has to jump all the way through. And then, once it's all the way at the top, eventually you can light it on fire, I guess. I actually don't think I've ever seen a dolphin jump through a flaming hoop, so we might want to extinguish some of that. But anyway, that's not really the point. The point is that it's this series of mini rewards along the route to the big payoff that that helps provide the right kind of hints.
Grad school.
I'm going to say life. Like you don't have to just say grad school. Like most of the things that we do are like this. We don't wait to get the big reward after we've inadvertently done the desired behavior. We get hints along the way.
You've clearly never met any of my students, but okay.
Since we don't have any robotic dolphins that we could be doing testing and training on, let's think through an example of doing reinforcement learning to try to teach a robot soccer player to score a goal. So this is supposed to be kind of a robot soccer pitch. This is the goal in blue, this is the ball in yellow, and this is the robot in black. And what we really want it to do is score in the goal. And that's worth 100. Again, just like in the dolphin case, it's very unlikely that the robot is going to spontaneously, drive around, hit the ball into the goal, experience the 100, and then say, okay, cool, that's what I'm supposed to be doing. So what are some things we could do shaping-wise? How can we modify this reward function so that it might encourage something in the direction of scoring the goal?
I think there are a couple of things one might do. I'll try not to overthink this. Well, in order to kick the ball, the circle with its circle feet has to get near the ball. So I could imagine putting some reward for being near the ball, wherever the ball is.
Cool. So you think like +1 is enough for that, or maybe?
I don't know, but let's start with +1.
All right. How do we define near the ball? There's going to be some kind of like epsilon ball around the ball.
Yeah, that makes sense. Or you could go all the way around and think about the distance you are to the ball is inversely proportional to the reward that you get.
Good point. All right. Let's look at your way of thinking about it first. So if we're getting reward, the agent is getting reward by virtue of being close to the ball. What's a good policy? A good policy might be to just sit in place or sit a little bit closer to the ball and just rack up the points.
Sure. So then you would need something else, like hitting the ball is worth some points.
Aha. Okay, that seems plausible, right? So if the robot is getting additional points, additional pleasure for getting close to the ball and then actually hitting the ball, yay, that was really awesome. But of course, by hitting the ball, it pushes the ball away, which is going to cause the near to the ball score to go down. So it's going to actually kind of be sad that it did that.
Sure. But then you would want to give it something for getting the ball near to the goal. So just like being near the ball is worth something inversely proportional distance, you want the distance of the ball to the goal to also be inversely proportionally related to distance.
Yeah, that makes some sense. Right. So now we want to be careful that the amount of bonus that the robot gets for pushing the ball toward the goal is going to be an improvement over the fact that it's now no longer itself near the ball.
Right. So I don't know, 2 times or something. I don't know. I mean, I don't know exactly what the right numbers are, but there you go, something like that.
So it seems like we could play with these numbers for a long time trying to get the behavior that we want. And there are a couple really interesting failure modes. So for example, if we have like hitting the ball being defined as making contact between the player and the ball, and you get, let's say, +10 for that each time, ignoring these other factors for a moment, then one thing that you often see when you ask reinforcement learners to learn in that kind of setting is you'll see the robot walks over to the ball, touches the ball, gets its +10, and it turns out if you want to get that +10 again, the best thing to do is just back off from the ball a little bit and then make contact with it again. And in fact, really what you want to do is go up to the ball and just shiver, right? Just like vibrate back and forth, blah, 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 so that you just keep getting +10s over and over and over again. You can make a lot of money that way, a lot more than you could make by scoring the goal, because you can do this, 30 or 40 times a second if you're a good wiggler. And so this ends up actually, even though this additional shaping information that we're defining is giving good hints, it's also creating spurious optimal policies.
Right. Well, I mean, it makes sense, right? People have been making money for thousands of years by wiggling. So
I guess that's sort of true. But in this particular case, what we have to do is somehow make it so that you can't have a money pump. You can't do arbitrage. You can't, by doing the good thing, undoing it, and then doing it again, get double credit.
I see.
So a natural idea is to actually say, all right, so if you're going to get plus 10 for hitting the ball, then letting go of the ball should be a minus 10, right? You should not be able to make a profit by repeatedly bumping into the ball. Does that make some sense?
It does, but my favorite part about that is how you called it an actual idea, which I suppose makes what I said not an actual idea. But yeah, okay.
Oh, I did not mean to imply that, or even
it's fine.
Say it.
It's fine. It's fine. It's fine. I see what kind of reward shaping you're doing. It's okay. In any case, what I guess is happening, so that makes sense. So you don't want to get into a place where you can get into a suboptimal positive loop. So you're going to say getting to the ball is good, getting away from the ball is not good. So you're going to learn to get to the ball and have to do something else that will get you even more reward, make it worthwhile backing away from the ball.
Right. Good. And I like that. I like the thing that you said about not wanting to create a suboptimal loop.
A suboptimal positive loop.
Ooh, because a suboptimal positive loop is actually going to cause the spurious behavior to happen. Right? If there's a way that you can actually do a sequence of actions and generate profit where there really shouldn't have been in the environment, then it's distracting, right? The agent is going to end up doing things that you didn't want it to do. So we have to avoid creating these suboptimal positive loops. And so a natural idea from, I'm going to say physics, and you could tell I'm an expert in physics because, I understand Bellman's equation, Einstein's Bellman equation, and that is that the idea of potential functions. So what I'm going to do is define potential functions and then show how we can use them to do shaping without actually messing up the optimal policy.
I look forward to it.
So the idea of potential-based shaping is going to be this. Instead of giving little bonuses for good things happening, what we're actually going to do is put bonuses on states of the world. Then when you achieve a certain state of the world, you get that bonus. And if you unachieve that state of the world, you lose that bonus. So everything kind of balances out nicely. So we'll write down an equation for that in a moment. But let's see if we can think about what state-based rewards might look like in the context of this little soccer example we were talking about.
Okay.
So the reward function, the official reward function, has us getting a plus 100 for scoring a goal. But we wanted to give hints. We wanted to give hints to the system for getting near the ball, hitting the ball, getting the ball near the goal. So we need to do that. We need to define that now in terms of the states of the world. So what would be some appropriate rewards that we could put in for that?
Well, I mean, I think they would be very similar to the ones that we were talking about before, right? If you're talking about states, you want to be in the state of the ball moving towards the goal, or the ball being near the goal, or you moving towards the ball or kicking the ball. Those are all states you would like to be in,
Yeah,
right?
okay. All right, so and the way that we were writing that before, I think, was something like 1 over the distance between us and the ball, and 1 over the distance between the ball and the goal. But now we think of these as being bonuses that are tied to the state, not values that we're getting for becoming close to the ball. So there's always this value, this potential that's keeping track of how close we are to the ball. And when we're close to the ball, it's a big number, and when we're far from the ball, it's a small number. And the reward that we're going to get is, as we change from state to state, how much more potential have we gotten. So to make this all work out, what we're going to do is introduce state-based bonuses, the sort of idea that instead of just giving little bonus rewards every time that you do a certain thing, instead we're going to keep track of what the state of the world is, and as we move to states of the world that are more desirable, we're going to get reward for that, which I guess is not that different from what we had before. But then we're going to have to subtract that off when we move away from those states. So the basic idea is we can still keep track of things like how near are we to the ball, and we can have a score that's associated with the inverse distance. But now the idea is that the rewards that we get for taking an action are going to be the increment that we get in this value instead of actually this value.
Right. Okay. So that's important, right? So that means if I went from being a foot, or let's say 10 pixels away from the ball to 5 pixels away from the ball, I get an increment of, let's say, +5 or 1 over the distance somehow. But for simplicity's sake, let's say like +5. But if I went from
Well, wait. Well, we can actually. These are numbers that I actually know how to do. So like this is like 0.1 and this is like 0.2. So we'd get a bonus of plus 0.1.
Oh, okay, good. I like that. All right, but that would mean then if we went from 5 pixels to 10 pixels, we would end up losing 0.1.
Right, and this kind of keeps the account balance in a good shape, right? Because it's saying that, sure, we'll give you a little bonus for doing good things, but you can't just continue to get that over and over again. If you relinquish it, we actually have to take those same points away so that we can give them back to you if you re-accomplish it.
Would it be more accurate to say it's not so much state-based bonuses, which I think you could argue is sort of what we were doing before, but it's sort of changes in state-based bonuses?
Oh, good. Yeah, I like that. So change in state-based bonuses.
Yeah, I like that.
All right, so we can continue to fuss with this, but I think it might be easier, believe it or not, to not get bogged down in details, but actually talk about this at a more abstract level.
Well, before you do that, can I ask a question?
Sure.
So I did make the claim that we were sort of doing state-based bonuses before. We just weren't doing the change in state. But I know I'm going to claim that of the 4 things you have written up there, score and goal, near the ball, hitting the ball, and ball near goal, is hitting the ball count as a state-based bonus or not?
It probably would want to be like touching the ball, like something that is actually something that's measurable in the state. Like hitting is a set of actions or is a sequence of actions.
Right, okay. So would that just be captured by near the ball?
Yes.
So, okay, that's fair.
Let's write down what the formal definition of these bonuses are, and then we can think again, if we want, about how we might define it for a particular problem. But let's look at the general form first.
Okay.
All right, so here's how we're going to define our modification of the reward function in this case of what we're going to call potential-based shaping. The potential is going to be defined by this function psi, is it?
Let's go with psi.
All right, so anyway, here's the idea. So once again, here's our Q function defined in terms of a reward function. And I did mess with this a little bit because I now made rewards dependent on the state that we end up in as well, because that's going to be helpful for keeping track of how rewards are changing.
Wait, does that change anything? That doesn't change anything, right? Does it?
It doesn't change anything in this Q function, no. So it's the reward plus the discounted value of the next state, and we average that over all possible next states weighted by the transition probability of ending up in that next state. So that's all the same. If we actually have a reward function that's not defined in terms of S prime, that's fine. This is just helpful for the notation. It doesn't actually change anything if we ignore S prime in the definition of RSA.
Oh, and in fact, if RSA doesn't depend on S prime, then you're just doing a convex sum over RSA, so you'll end up with RSA. So you'll get back what you were before.
Exactly, right. So this R, that's right. The reward function pops back out, which is sort of the opposite of what we just did, which is we shoved it in there.
Okay.
Good. All right. And so now our new reward function, R prime, that we're going to use is going to be the old reward function for state action pair minus the potential of the state that we're leaving plus the discounted potential of the state that we're entering. So this difference here between the potential of the state that we end up in and the potential of the state that we left is the bonus that we get, the amount that we're getting warmer and we're getting closer to good.
Okay. So looking at it, okay, so I see. So let me make certain I got the intuition here. So let's ignore the minus psi of S and just think about the plus gamma psi of S prime. You're saying that every time we enter into some state, S prime, we're going to get that little bonus, which is what we've been talking about before. But now I got to account for the minus psi of S. Well, the minus psi of S is just a way of saying, yeah, but whenever I leave a state, I have to lose that bonus. And that's your way of avoiding those kind of suboptimal positive loops.
Yeah, exactly right. It's sort of like, good bookkeeping or accounting, right? We have to make sure that sure, we made a transition from state S to S prime. We get this advantage of being in S prime, but we have to have lost the advantage of having been in S because we're not there anymore.
Okay, so this makes sense.
Great. Okay, so what we need to do now is figure out what does the new Q function look like when we've made these revisions to the rewards as a function of the old Q function.
Okay. I think I know the answer.
All right. So you think you're ready for a quiz, or do you need any kind of additional explanation of what I'm asking?
No, I think I know. You defined. We know what Q of SA is. We're going to change the way the reward function works to have these potentials. And so that's going to change what Q of SA is. It's going to be now called Q prime of SA. And you want to know if there's some nice way that we can describe Q prime of SA, I guess in terms of the old Q of S of A?
That's right. That's right. And in fact, there is a nice way of explaining it. Or it's not of explaining it, but of defining Q prime in terms of Q.
Okay. I think I know the answer. We'll see.
So you want to help us think through what this could be?
Yeah, so I think I know the answer because I think I know how to get the answer because I think it's like other times we've done this sort of trick. And the key part is noticing that we are adding and then subtracting off the things that we just added and then adding the thing we just got, but then subtracting that off. And so every time we go through a state, action, reward, we're going to end up adding a potential and then subtracting the same potential on the next step.
Here's a useful way to kind of visualize that. So we're going to go through some sequence of states, S prime, S double prime, S triple prime, S quadruple prime, and so on. And in this Q version of the Q function, we're getting the sum of the rewards for those states. So we have like a reward that happens here, and a reward that happens here, and a reward that happens here. But these are going to be discounted and summed up to get our Q. And now we're wondering, well, what happens if we replace this R with this new R prime? It still has, R in it, but now it's going to have this take away psi, give me some gamma psi prime, S prime.
Give me some psi. Yeah, exactly.
Yeah. High, low, on the psi. All right. So this first reward, in addition to the R part, we're also going to get the minus psi and the plus gamma psi. So let's just add that in here for the transition from S to S prime, but we'll also have to add it in there for the transition from S prime to S double prime. So the second reward is gamma times whatever the reward is, which is what it used to be, minus the psi S prime plus the gamma psi S double prime, and so on. For each of these rewards is going to get replaced by what it was, plus the discounted psi minus the psi.
Right. So if we look at that, so good. So writing that down confirmed my thought. So first thing you notice is that things start canceling each other out.
Right. So in particular, this gamma psi S prime and this gamma times negative psi S prime disappear.
Right, and then that's going to happen again.
It's going to happen again on the double prime, right? And the triple prime, and the quadruple prime, and so forth. And then all we're going to be left with are the R's themselves, which we were writing as Q, and this weird little extra minus psi S in the very beginning.
Right. So then I think that we can write Q prime S of A as being equal to Q of S of A minus psi of S.
Nice.
And there's only one little bit of bookkeeping we have to argue our way out of, and that's the fact that we are getting rid of everything in the middle except the things at the beginning and the things at the very end, the thing at the very, very end.
Right. So there's some kind of gamma to the infinity psi of S infinity kind of thing at the end. Right.
But if gamma is less than 1, then something less than 1 to the infinity is just 0.
Right, as long as our psi, I guess, is bounded, which we didn't say, but it's true.
It better be bounded. So then it's 0, so we can ignore it. And that's cool because that's what always happens whenever you have a telescoping sum.
Yes, even though this was an infinite telescoping sum. Very cool. All right, so does this make some intuitive sense at the end of the day? So our new Q function is just like our old Q function, except it's shifted downward by psi S. Like, this downward kind of bothers me a little bit.
Well, so it was bothering me too, but actually I think it doesn't bother me now. So what you're saying is the true value of being in a state and taking an action is actually whatever the value is minus the potential you're going to lose. Because you need to account for everything, right? You need to account for not just the reward that you get for being in a state and all the discounted rewards you're going to get thereafter, but for any potential that you're going to lose along the way. And so psi is that potential that you're going to lose by leaving the state. So Q basically captures what you're getting for being in a state and then what you're going to get from that point on, right? Assuming you behave in a particular way. Well, what's going to happen from this point on? Well, you're going to get the reward that you got in the state like before, but then you're going to lose whatever magic psi we gave you for entering into the state. So we have to account for not just the present, but also the future.
Right.
So The future requires getting rid of the potential. So I think that's fine. So it kind of makes sense to me. I kind of wish it weren't that way, but it does make sense if the reward is actually you're going to get a little bit of extra bump and bonus. Right? So another way of thinking about it is you got r prime of SA S prime up there is equal to r of SA minus psi of S plus gamma psi of S prime. Well, if you were to write down what r prime of SA was, it would just be r of SA minus psi of S, right? If you were to ignore the S prime part, because the S prime part only matters with the discounted future. So then Q prime is just the rewards that you would get minus the potential you're about to lose. So I think it works out just fine. It makes them.
I guess so. I guess I just wondered, I mean, why wouldn't it be plus? Like, why wouldn't it be the case that, the Q value for being in a state is what it used to be, but we got this extra bonus for having gotten to S in the first place?
Because we're going to lose the bonus.
We're going to lose the bonus. And so we have to pre-lose it?
Well, I don't think you're really pre-losing it. I mean, what's really kind of happening, I think, is that you've kind of got a new R of S of A, and that R is including the psi. And so you've got to subtract it off to get back the original R that you had.
All right, well, so let's just to be certain that we're comfortable with this, maybe we should do the algebra to make sure that this all really does balance out. All right, so I've just written out our equation for Q prime and substituted in the definitions that we think are true, what the new Q prime is in terms of the old Q, and what the new rewards are in terms of the old rewards. And so if this works, if we can do a bunch of if and only ifs that actually bring us to something that we know is true, then we should be good.
Okay.
So, all right, how can we do have an equation for Q. We don't have an equation for Q minus psi of S, but maybe we can cancel some things?
Oh, I can see two things we can cancel.
All right.
Okay, so the first psi of S on the left side of the equal sign?
Yep.
That matches up with the first psi of S right next to R. Yes, right there.
Yeah, because we're summing this over all next states, all next S primes, and this sums up to 1. It's a convex combination.
Right. So that means effectively you could take it out. It doesn't depend on S prime anyway. And they go away. Good. So now we got Q of SA on one side. And then you can actually handle the next one. If you look at the next psi of S prime, the gamma of psi of S prime, well, that matches with the minus gamma of S prime inside the max, because that max is multiplied by gamma.
Good. Right. Yeah. So it's interesting. And the max itself is not impacted by this quantity because it doesn't depend on A prime.
Right. It is in fact a constant.
So we can actually take out this constant, and it actually cancels this one. And look what we're left with.
The original equation.
Ta-da! We're left with the original Q equation, which we know is true. And so this is true if and only if the original thing is true. This is an actual solution to the Q equation, the Bellman equation. And so, right, this is what happens to the Q function. It's the old Q function shifted down by the potential function.
Right, and at no point do we divide by 0, so everything is great.
Right, and how do we know that we still have the same policy, the same optimal policy?
In which case?
So we know we have some optimal policy for this Q function. This new Q function, Q prime, has an optimal policy. How do we know it's the same?
Well, because it's just the original Q function, and you're just being shifted around by a constant, and so it doesn't change the max, and therefore it doesn't change the optimal policy.
Exactly. Awesome. All right, so this now gives us 3 total different ways of messing around with rewards to give us new Q functions that don't actually change the policy.
That's really nice. So I have a question.
Sure.
You didn't write anything down here about any restrictions on the potential function.
That's right.
Does there have to be any restrictions on the potential functions? Maybe potential restrictions potentially?
I'm going to say no, because it's all going to end up being okay and canceling out. So there's a sense in which you actually not changed anything by throwing in one of these additional potential functions, but maybe it can help us learn faster. So let's look at an example where this might matter.
Okay.
So it's helpful to think about how we would use this potential function idea in the context of Q learning instead of just solving Bellman equations like we had a moment ago. So in the setting of Q learning, we're going to be keeping some Q function, QSA. And each time we get a state action reward next state quadruple, we're going to update our state action pair for the state action pair that we just left to be a little bit more in the direction of the reward plus the discounted value of the state we end up in. And this reward now we're going to use the real reward, but now we're going to shift it around, mess it around with this potential function. So we're going to take the actual reward, subtract the potential for the state that we're leaving, and add the discounted potential for the state that we're arriving in. And so this is going to be how we do our updates. And so if we run this version of Q-Learning, what should happen in the limit?
The right thing.
Yeah, so it should actually solve the original MDP, the one with just R here, and it should ultimately ignore these psi's. So there's a sense in which we don't really care what these psi's are. So what if we choose like this one? What if we say psi of s is the max over all actions of the optimal Q function, Q star, for that state action pair?
You mean the actual true value of being in the state?
Yeah.
Oh, well, first off, if we choose psi to be that, then we're already done.
Well, so yes and no, right? I mean, we only can do this if we've already solved the problem. So admittedly, this is an unrealistic thing to be able to do. But what does it do to Q? What does Q end up being in this case?
0.
Is that obvious? QSA is going to be Q star of SA minus psi of S, right? That's what we figured out on the last slide. And this psi of S is exactly max A Q star SA.
Which is Q star SA.
Not exactly, right? So QSA for the optimal action is 0.
Oh, you're right. I'm sorry. What I just said is true for when you take the optimal action. It is 0.
Right. So QSA in this case is going to be 0 if A is optimal.
And it'll be less than 0 otherwise by a constant for each action otherwise.
Right.
Yeah.
By the amount that it's suboptimal.
Yes, that's exactly right. By the amount that it's suboptimal.
So this is kind of cool. So if you think about initializing your Q function to 0, which we often do because, what do we know? Then it should start off actually doing the right thing. It should maybe take some of the non-optimal actions, discover that they have a value less than 0, and then after that, just take the best ones. So this gives you an incredible leg up on the learning problem. One other thing I want to point out here, this is kind of cool, and this is maybe why potential functions are helpful and why it can help speed up learning. Eric Rewara showed that the series of updates that you get by running Q-Learning with some potential function is actually exactly the same as what you'd get by running Q-Learning without a potential function, but with the Q function initialized to what the potential function would have been.
So you get the same in the sense that you get the same answer, or you get the same in the sense that it takes the same amount of time?
It goes through the same series of action choices. So it's going to do the same things forever. But yeah, the actual Q functions that you get are different in the two cases.
Okay, I meant the same thing in terms of policy, which I guess had to be true. So
yeah, it's not so. But not only does it converge to the same policy, which we knew was true, but it's actually going to have the same policy at every step during learning.
Right. So that makes sense. Okay, cool. Oh, sure, because psi is just a constant, really, with respect to any given state.
Right. That's right. Which is having an impact, this shift impact on what the Q values are converging toward. Yeah. So
that's kind of neat.
Yeah, it's neat. It's a cute proof technique as well. So I guess one way of interpreting this is, potentials are really cool. It's just like initialization. Another way to interpret this is, who needs potentials? You can always get the same effect by Q function initialization.
Well, I think it says something else too. It says that whenever you randomly initialize your Q function, you are in fact asserting a particular potential, which just cannot be the right thing to do.
Wait, so what do you mean by that?
Well, this argues that because sometimes, what are you going to do? You got to start out somewhere, so you just randomly initialize Q functions, put random values in every Q function. But that's like saying that, since that's equivalent to having a potential function, you're saying that where you randomly chose to put high values versus low values, you're saying those are places you ought to be, or places you ought to start out trying to be anyway. So that would argue against random initialization.
Because it's going to be, it matters, and so if it matters, why be random? I mean, one reason to be random, even though it matters, is because you don't know. If you always say give it 0, or you always give it plus 1,000 or something like that, you're biasing it as well in a very consistent way that's easy to fake out, right? Like, it's easy to make up an example MDP where that's going to be the wrong thing. Whereas if it's random, maybe it'll work.
My guess is, though, that if you integrated over all the ones that were wrong versus all the ones that were right for any given random thing, for any given fixed MDP, if you didn't know what it was, that number is going to be big. So I think it argues for you shouldn't be randomly initializing Q functions.
All right. That's not an unreasonable thing to say. I mean, because basically you're injecting knowledge, and you should not inject noise. You should inject knowledge.
Right. Actually, that's exactly the right way to put it. Knowledge and noise don't both start with N. Only noise does. That feels like a saying. Knowledge and noise both sound the same, but knowledge starts with K, like okay, and noise starts with no, like N-O.
No. I did not know that. Which is the beginning of knowledge. Okay, all right. I fear that we are off track. So what was the punchline of all this was that, well, your punchline was you don't want to randomly initialize your Q functions. My punchline was just that you can actually inject various kinds of knowledge in here, and it could have an impact on learning time. This doesn't actually show that it has an impact, but empirically it often does. There are some results that actually show that if you initialize your Q function optimistically, but not too optimistically, you can actually bound what the learning time is going to be in terms of that. But that's kind of a story for another time. I think at this point we've said what we were going to say about messing with rewards. So maybe we should do a what have we learned?
Okay. I'm a big fan of that.
All right, Charles. So what have we learned?
We have learned that unlike Texas, you can mess with reward functions.
And what does that mean?
Well, it means that you could take the rewards that you're given and you can modify them to still get the same policy, but maybe to learn it more quickly. You can shape them and thus shape the experiences of your agent.
And I think we talked about 3 different ways that we can do that. Do you remember what they were?
I remember one of them, potential functions.
Sure, that was the last one.
So also you can just do a shift. You can just add a constant, and it doesn't matter what that constant is, so long as it's a constant. And you can scale them. So, but you want to scale positively. So it does matter what that constant is.
Otherwise, we can swap max and min by accident.
Right. But I think the difference between the third one and the first two is that the first two sort of don't change anything at all. They're just, a kind of, I don't know if it's affine, but they're just a kind of simple linear changing of the function. But the potential functions are sort of set up to help you learn faster, not just learn the same thing.
So have we learned anything else?
Well, I think we learned something, or at least there was a subtle thing we should have learned, which is, well, potential functions can help speed things up, but we got the potential functions by just talking about shaping rewards, by just trying to change them in a way that captured the parts of the space that were better than others. This is kind of pre-potential functions. So I would say we learned about reward shaping in general, and that we learned that you can do it really wrong.
And what happens when it goes wrong?
Well, when it goes wrong, you end up in these kind of suboptimal positive feedback loops. And in fact, the answer to that was potential functions. And that keeps us from getting into these loops because we subtract off the things that we gained.
Sure. Okay. I buy that.
Okay. So that's good. So we learned about reward shaping in all of its various forms and learned that it can hurt you and that potential functions are a way to avoid that. And potential functions are kind of magical.
They do some really clever things. Probably good if on the homework we look at some ways of building potential functions and which things tend to speed up more than other things. So there's some nice empirical questions there, and we should probably dive into that.
Yeah, I like that because, I think, one could walk away from this thinking, well, potential functions are just magical, they work, and everything's okay, except clearly there must be better potential functions than others. Must be some that have no real impact on learning and some that, have no impact on the speed of learning. In some sense, all we showed is that potential functions don't prevent you from finding the right answer, but presumably you could come up with a potential function that actually hurts.
Yes. Right, that it could lengthen the amount of time before good behavior is learned.
Right. Okay, cool. So luckily we have homework for that, and the students can figure that out on their own. That seems great.
All right, cool. Well, thanks very much for going through this with me.
Oh, no. Thank you, Michael. I enjoyed every moment of it.